Hi, I'm Toru Kajigaya of Tokyo University of Science. First of all, I'd like to thank all organizers for giving me a good opportunity to talk. In this video, I will talk about Hamiltonian stable Lagrangian tori in complex hyperbolic space. This is the plan of my talk. First, I introduce the Hamiltonian volume minimizing problem, and I will review related results in the complex Euclidean space and in the complex projective space. After that, we consider the same problem in the complex hyperbolic space. And in the second section, I will explain related geometry of CHN. And also, I provide many examples of Hamiltonian minimal Lagrangian semifold in CHN. In the third section, we focus on the Lagrangian torus in CHN and investigate the Hamiltonian stability, Hamiltonian volume minimizing property of the Lagrangian torus. And let us start from introduction. The classical isometric inequality for simple closed curve gamma in the Euclidean plane or the standard sphere or the hyperbolic plane implies that the square of the length of gamma is greater than or equal to this quantity. Here, a gamma is the area enclosed by gamma. And it is also known that equality holds if only if gamma is a geodesic circle. This implies the following fact. If you fix the area enclosed by gamma, then the right-hand side is constant. So this inequality implies the geodesic circle has the least length among simple closed curves with the same area. For example, if you deform this red curve to the blue curve so that the area enclosed by blue curves is the same as the area enclosed by the red curve, then the length of the red curve is smaller than the length of the blue curve. As a generalization of this fact, we will introduce the following notion. Let M omega be a simplex manifold of real dimension 2n and L a compact Lagrangian semifold in M omega. That is the semifold satisfying that the restriction of omega is vanishing and the dimension of L is equal to the half of the dimension of M. And we endow M with a Riemann metric C. For example, you can define an almost scalar metric on M. Then we say L is Hamiltonian volume minimizing with respect to Z if the volume of L is smaller than or equal to the volume of FL. Here, FL is a deformed Lagrangian semifold by a Hamiltonian isotopy on M. Here, Hamiltonian isotopy is a simplex morphism on M, which is obtained by a flow of the time-dependent Hamiltonian vector field. So we want to consider volume minimizing Lagrangian semifold under the restricted deformation that is Hamiltonian isotopy. And then we should remark that there is a notion of special Lagrangian semifold in the Calabian manifold. In this case, it is automatically volume minimizing in its homology class, so it must be Hamiltonian volume minimizing. So the notion of Hamiltonian volume minimizing Lagrangian semifold is a weaker notion of the special Lagrangian semifold. And the basic problem is to find a Hamiltonian volume minimizing Lagrangian semifold in a specific simplex manifold, for example, in the Kähler manifold. For example, if M is a complex plane or CP1 or CH1 with the standard Kähler metric, and L is a geodesic circle, and this is exactly the previous example. Any Hamiltonian isotopy F preserves the area enclosed by gamma because F is a simplex morphism, and in this case, the simplex form is exactly the area form on M. So therefore, the isoparometric inequality implies that the geodesic circle is Hamiltonian polyminimizing. The generalization of this fact, Kleine and Wu pointed out that there exists a Hamiltonian polyminimizing Lagrangian in CPN. More precisely, the total geodesic RPN is such example. We should remark that there is no stable minimal Lagrangian semifold in CPN in the classical sense. So this result is surprising. Moreover, O and Hajime Ono prove that the standard torus in CN and the quotient torus in CPN are all Hamiltonian stable. That is, it can be locally volume minimizing under the Hamiltonian deformations. Moreover, they conjecture that these tori are Hamiltonian volume minimizing. However, it was proved that the conjecture is false in general. In fact, Viterbo gave a counterexample for the torus by using a result of Chekhanov. And by generalizing his example, Ire and Ono showed that almost all Lagrangian standard tori in Cn and CPN are not Hamiltonian volume minimizing when the dimension is greater than or equal to 3. There is still an open problem for some tori, including the Clifford torus, which we discuss later. But this is a related result on the, especially in the complex Euclidean space and the complex projective space. How about hyperbolic case? As I mentioned, the isoparometric inequality holds even in the hyperbolic plane. However, we do not know any higher dimensional analog in the sense of HVM Lagrangian. Moreover, it is well known that any minimal Lagrangian semifold in the Keller manifold of negative Ricci curvature is strictly stable. So the stability of Lagrangian semifold may depend on the Ricci curvature of the ambient space. So it is a reasonable question to consider the Hamiltonian volume minimizing problem in the hyperbolic case. So a natural higher dimensional setting is when M is a complex hyperbolic space and L is a compact Lagrangian semifold in CHN. Recently, I investigate the Hamiltonian stability and HBM property of some Lagrangian semifold in CHN. I focus on Lagrangian torus, more precisely Lagrangian torus orbits in CHN, and proved the Hamiltonian stability and non-Hamiltonian volume minimizing property of some torus orbits. I will explain the details of this result in the following slide, and also I will explain how to prove this result. In the first section, I will explain related geometry of CHN, and by using the geometry, I will provide a mini example of reasonable Lagrangian semifold in CHN. It is well known that the complex hyperbolic space is realized by several ways. For example, CHN is obtained by a quotient of some Lorentzian manifold, so-called anti-digital space, or we can identify CHN with a homogeneous space. More precisely, it is a typical example of a Hermitian symmetric space of non-compact type. It is also well known that CHN is realized as a bounded domain in the complex Euclidean space. It is so-called the pole model. However, in this talk, I will use another realization of CHN. It may be a well-known fact that CHN is simply diffeomorphic to CN, and this means that the simple geometry of CHN is completely the same as CN. Indeed, we can construct an explicit simple diffeomorphism between CHN and CN. More precisely, it is given by this map. I don't give details of this map. However, I just remarked that this map is regarded as a canonical simple morphism between CHN and CN. In fact, we can generalize this map to any Hermitian symmetric space of non-compact type. And also, we can give a characterization of this map in the context of Hermitian symmetric space. Please refer to my recent paper. Anyway, because CHN is symplectic diffeomorphic to CN, any Lagrangian sum-manifold in CN is regarded as a Lagrangian sum-manifold in CHN. Moreover, it is interesting that the symplectic morphism phi is in fact K equivalent, where K is a maximal compact subgroup of the automorphism group of CHN, and K naturally acts on CHN, and it acts on CN by the isotropy representation. More precisely, since K is regarded as an isotropy subgroup at the origin O, so it acts on the tangent space at the origin, and we identify the tangent space with the complex Euclidean space. In particular, it turns out that there exists a correspondence between compact homogeneous Lagrangian sum-manifold in CHN and compact homogeneous Lagrangian sum-manifold in CN. For example, there is a natural torus action on CN, and the orbit is a standard torus. Corresponding to this, we have a natural torus action on CHN and the corresponding Lagrangian torus in CHN. Furthermore, through the map phi, we can find more geometric similarity between CHN and CN. For example, each K orbit in CHN corresponds to our K orbit in CN. More geometrically, the K orbit coincides with the geodesic hypersphere of radius r in CHN, and the corresponding K orbit is exactly the standard hypersphere in CN of some radius. Moreover, from a symplectic geometric point of view, these orbits actually coincide with a regular level set of the moment map of the S1 action, where S1 is obtained by the center of K divided by normal subgroup. In particular, we obtain Kähler quotient space of the S1 action for CN and CHN. It is an interesting fact that the Kähler quotient spaces coincide with each other as a Kähler manifold. In particular, we have the following correspondences. If we have a Lagrangian sum-manifold in CHN, then we obtain a Lagrangian sum-manifold in CN by the map phi. If furthermore, the Lagrangian sum-manifold is S1 invariant, then it must be contained in the regular level set of the moment map of S1 action, and the corresponding Lagrangian is also S1 invariant. Moreover, by taking the quotient of the S1 action, we obtain a Lagrangian sum-manifold in the Kähler quotient space. Conversely, if we have a Lagrangian sum-manifold in the Kähler quotient space, by taking the image of the projection, we obtain a S1 invariant Lagrangian in CN, and this provides S1 invariant Lagrangian in CHN. Let us consider a Riemannian geometric property of Lagrangian sum manifold in the Kähler manifold? Because that a Lagrangian sum manifold in the Kähler manifold is said to be Hamiltonian minimal if it is a critical point of the volume function under the Hamiltonian deformations. Moreover, the Hamiltonian minimal Lagrangian is called Hamiltonian stable if the second variation with the volume functional is non-negative for any Hamiltonian deformation. We remark that the Euler-Lagrange equation for Hamiltonian minimal Lagrangian is given by this equation. Moreover, if L is Hamiltonian volume minimizing, then it must be Hamiltonian stable and Hamiltonian minimal. So in order to find the Hamiltonian volume minimizing Lagrangian sum manifold, to find the Hamiltonian minimal Lagrangian is the first step. There are some useful facts on the H minimality. The first fact is said that any compact homogeneous Lagrangian in the Kähler manifold is Hamiltonian minimal. This is because if L is homogeneous, then this function must be constant. And by using the divergence theorem, combining with the compactness, this function must be 0, so it is Hamiltonian minimal. And the second fact is due to Yu-Shindon. Suppose a compact subgroup Z in the automorphism group acts on a Kähler manifold in a Hamiltonian way with moment map mu. And suppose also L is a G invariant Lagrangian sum manifold in M. Then it's well known that L is contained in a level set of the moment map for some element C in the center of K. Moreover, if G orbits contained in mu inverse C are mutually isometric, then we see that the H minimality of L in the Kähler manifold M is equivalent to the H minimality of the quotient Lagrangian sum manifold in the Kähler quotient space. Applying the previous fact to our setting, we get an H minimal Lagrangian in CHN from an S1 invariant H minimal Lagrangian in CN. And this is equivalent to H minimal Lagrangian in CPN minus 1. As a summary, we have the following correspondences. For example, the standard torus in CN is a typical example of H minimal Lagrangian. It is also true that the corresponding Lagrangian torus orbit in CHN is Hamiltonian minimal. We remark that there is no compact minimal sum manifold in CHN and CN. So these examples are never minimal sum manifold. However, we know several examples of H minimal Lagrangian in CN. So this example provides many examples of H minimal Lagrangian in CHN through the map 5. We stop here the first section, and in the next video, I will investigate the Hamiltonian stability and the HBM property of the Lagrangian torus orbits in CHN. Thank you for listening.